We're going to start this chapter by actually defining a wave. Now, a wave is simply a disturbance or an oscillation that travels along a medium from one point and propagates away. So, for example, in the top, you see a stone thrown in the pool over here, and then that creates a disturbance, causes the water to oscillate up and down, and that oscillating pattern just propagates outward. And beneath that, you see a rope where someone is inducing an oscillation in a rope, and that pushes the rope forward along the rope. So that is an oscillation that is propagating forward. You have yourself a wave. Now, we often look at a wave and say, that looks like this whole wave is just moving this direction. So you have this large disturbance and the wave itself is moving. A common example of this would be something like an ocean wave. You say that the ocean wave moves onto the shore. Well, that's not exactly true. What's really happening is you have individual points here that are moving up and down, and they just keep oscillating up and down. Likewise, you have this point which oscillates up and down, and this point which oscillates up and down, and so on. And so really, a wave is nothing more than a series of oscillations in a pattern. That's really what a wave is. Now, we need to define two different types of waves that we are going to look at in this video. The first is a pulse. A pulse is one single set of oscillations, meaning you have your rope is in equilibrium, and then you have a disturbance, and it comes back down, reaches equilibrium, and stays there. That is a pulse. But a continuous wave would be a series of pulses, at regular intervals. Now, if we actually go through and study a single wave pulse, which begins with just a simple vibration that's transmitted through internal forces in the medium, we can see some really interesting things. How do waves move forward? Well, let's consider this point right here. This point has kinetic energy, and it is moving upward. But that point cannot move upward unless it drags the next point along the rope along with it. And so all of a sudden, the first point's upward motion kind of drags this next point along with it and gives some energy to that second point. And so we can say that this is a wave is a transport of energy. Every time you have a point that moves, it forces the point right after it to move as well. Now this works, here in the picture we're showing a pulse, but of course this works for continuous waves as well. Now, let's talk about the wave itself. Here we have a continuous wave. We're going to define a few parts of the wave. First of all, there's the amplitude. The amplitude would be the maximum displacement. So, any point along here, this would be your amplitude, the maximum displacement. Okay? Now, sometimes you have a maximum positive displacement. So here this would be positive A. And when you do have that maximum positive displacement, we call that a crest. But then being a wave, it oscillates, goes back, and it dips back down to a maximum negative displacement, or negative A. We call those troughs. Okay, another important part of a wave is the wavelength. This is basically the size of the wave. If you take a wave and you go from the peak of one crest to the peak of the next crest, that is a wavelength. Similarly, you could also go from peak of a trough to the peak of the trough. That would also be a wavelength. Or if you say beginning of a sine wave, there's a sine wave, one full sine wave. We've completed one cycle. That is a wavelength as well. In fact, you can pick any point you want to, and the identical point in the next wave will be exactly one wavelength away. The next important point is the frequency and the period. Now, the period is the time for one oscillation. In other words, how much time does it take for the wave to go from a crest down to a trough, back to a crest? That is the period. Now, so basically, the period is the time per oscillation. The frequency would be the inverse of that. So frequency is 1 over the period. So the period is time per oscillation. Frequency then would be oscillations per unit time. In other words, we're talking about how many waves pass by in 1 second. And then last but not least, we have the forward velocity of the wave. No, the particles themselves don't move forward, but the energy of the wave does move forward. And that's what we're talking about with the wave velocity. And how do we calculate that? We calculate that using the wave equation, one of the most important equations you'll see this semester. So definitely take note of this one. The velocity of a wave is going to be the product of the wavelength and the frequency. I should mention here, I forgot to mention this earlier, the wavelength, this upside down Y is what it looks like. That's the Greek letter lambda, and it's the symbol we're going to use for wavelength. All right, so here's an interesting thing that happens with a single pulse. So we have a single pulse that is emitted and moves to the other end. If the other end of this rope is fixed, like here it's nailed down, then what's going to happen is this pulse will hit the fastened end, and then it will reflect back inverted. It will become upside down. But if this other end is not fixed, but open, allowed to move freely, then that pulse will reach the other end, cause the end to move, and then it'll reflect the wave back, but it will not be inverted. It will remain upright. So that's an important point that we need to bring up for to discuss waves and pulses later on.